Hello there, and welcome to the Sleepy Space Channel. The 12 light years between here and Tau Ceti are the safest part of the journey. Interstellar space is emptier than any vacuum our species knows how to manufacture, and at 1% of the speed of light, it barely touches a ship passing through it. The trouble is waiting at the far end. Tau Ceti is surrounded by a belt of debris holding more than 10 times the comets and asteroids of our own solar system, and a vessel that crossed 12 light-years untouched has to slow down inside it, over years, with its margins already spent. Tonight, 1,200 years in a single direction, and everything a ship full of people would meet along the way. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. It is a crossing that would begin long after tonight and end long after that, and it asks nothing of anyone listening. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. A voyage to Tau Ceti begins with a single number, and everything else on the ship is downstream of it. The star lies about 11.9 light-years from the Sun. Crossing that gap in 1,200 years requires an average speed of very close to 1% of the speed of light. That works out to roughly 2,975 kilometers per second, sustained without interruption for 12 centuries. The two figures are not separate design choices. They are the same fact, written down twice. Once the schedule is fixed, the speed is no longer negotiable, and once the speed is fixed, the schedule follows from it automatically. A mission plan for an interstellar crossing is, at its foundation, one number wearing two different costumes. That number is worth holding on to, because it makes the whole voyage legible. At 1% of light speed, a ship covers 1 light-year every 100 years. Light-years elapsed equals centuries elapsed. Nothing about the crossing requires arithmetic more complicated than that. A child born aboard in the 3rd century of the voyage can be told, accurately, that the ship has come 3 light-years and that it has 9 to go, and that both of those statements will still be true in the same simple way when the child is old. 1% of the speed of light sits at a very particular place on the ladder of speeds our species has actually achieved. The fastest machines we have ever released into deep space leave the solar system at about 17 kilometers per second. A ship traveling at 1% of light speed is moving roughly 170 times faster than that. It is not a modest improvement on anything. It is a different category of vehicle, and no combination of chemical rockets and gravity assists reaches it, or comes within many orders of magnitude of reaching it. The concepts that reach 1% at all are fusion concepts, and 1% is the low end of what they claim rather than the high end. That is precisely why the number keeps recurring in serious mission studies. It is the slowest speed at which an interstellar crossing finishes inside a span of time that a continuous human society could plausibly be asked to maintain. Underneath the speed sits a piece of arithmetic that shapes everything about the vehicle's size, and it is worth stating plainly because it explains why interstellar mission designs look the way they do. A rocket carries its own propellant, which means it must accelerate the propellant it has not yet used. That requirement compounds. To reach a given speed, the ratio of the ship's starting mass to its final mass has to be large, and to reach a given speed and then get rid of it again at the far end, the ratio has to be roughly the square of that. Stopping is not the second half of the mission. It is the expensive half. Every kilogram that arrives at Tau Ceti at rest was paid for at launch, at a price set by a calculation nobody aboard will be in a position to revise. The total velocity change involved is about 6,000 kilometers per second. 3,000 to get up to speed, 3,000 to get rid of it. Between those two events, the engines do nothing at all. For something like 99% of the 1,200 years, the ship is coasting, which is to say that a generation ship is, for almost the whole of its working life, a thrown object. It is not being driven anywhere. It was aimed once, at the beginning, and released. That coasting phase deserves a moment, because it is easy to picture an interstellar voyage as an act of continuous effort, and it is nothing of the kind. The engines run at the beginning, and they run again at the very end, and in between they sit cold for a length of time comparable to the whole of recorded history. There is no throttle to adjust, no course to hold against a current, no drag to overcome. Whatever velocity the ship has when the first burn ends is the velocity it keeps. The interstellar medium is far too thin to slow it measurably, and there is nothing else out there to push against it. The vehicle simply continues, at a constant speed, in a straight line, for 12 centuries, exactly as an unattended object would. What that means practically is that the ship's propulsion system spends the overwhelming majority of the mission as stored equipment rather than working machinery. It is preserved, inspected, and never used by people who have no direct evidence that it still functions and no way of testing it that does not spend some of the propellant they cannot spare. The first time anyone finds out whether the engines still work is the moment the mission depends on their working. Which brings us to the thing that has to be aimed at, and this is where the voyage acquires its first genuine complication. Tau Ceti is not where it appears to be. Stars move. Most of them move so slowly against the background of the sky that the motion is invisible over a human lifetime, and the constellations look permanent because nobody watches them for long enough. Tau Ceti is not one of the slow ones. It crosses the sky at about 1.9 arcseconds per year, which places it among the faster-moving stars in the local neighborhood. On any human timescale, that is nothing. Over 1,200 years, it is more than half a degree, a stretch of sky slightly wider than the full moon looks from the ground. It is also coming toward us. Its motion along the line of sight is about 17 kilometers per second, in the direction that closes the distance rather than opening it. Put the two motions together and the picture becomes clearer. The sideways drift, converted from an angle into an actual speed at the star's actual distance, works out to about 33 kilometers per second. Combined with the 17 along the line of sight, Tau Ceti is moving through the neighborhood at something close to 37 kilometers per second relative to the Sun. That is a brisk pace for a star. It is also a clue about the kind of star it is. Older stars have spent billions of years being gently stirred by every mass they have passed, and they tend to move faster and less tidally than young ones, on orbits that carry them further above and below the plane of the galaxy. Tau Ceti's motion is consistent with an old star, and everything else known about it agrees. Set that speed beside the ship's speed and the proportions become obvious. 2,975 kilometers per second against 37. The ship is moving about 80 times faster than its destination. The aiming correction is real, and it is small, and it is entirely unforgiving of being got wrong. So the navigation problem at the start of the voyage is not the problem of pointing a ship at a star. It is the problem of pointing a ship at a prediction. Somewhere in the ship's memory there is a set of numbers describing where Tau Ceti will be in the year 1200, and the accuracy of the arrival depends on how well the star's velocity was measured in the years before departure. The margin for error is not generous. At a distance of 11.9 light-years, An aiming error of a single arcsecond puts the ship about 3.5 billion kilometers off target, which is roughly the distance from the Sun out to Uranus. That is a miss that could be corrected, but only by somebody willing to spend propellant that was allocated to something else. Mid-course corrections are cheap in fuel and expensive in every other sense. The correction is made by a crew that will never learn whether it worked. They adjust a trajectory, they log the burn, and the confirmation arrives centuries after the last of them has died. It is one of the mission's quieter structural facts. Almost every decision made aboard is a decision whose outcome belongs to somebody else. The ship can at least know where it is. Navigation using the steady pulses of rotating neutron stars has been demonstrated in orbit around the Earth, fixing a spacecraft's position to something like 10 kilometers by timing signals from objects thousands of light-years away. That precision is far better than an interstellar crossing needs. But knowing where you are does not solve the problem of knowing where the destination will be. Those are separate questions, and only the first one has a clean answer. So the ship departs carrying an estimate. Not a destination, an estimate of a destination, made by people who will be 1,200 years dead when it is finally tested. Everything else aboard, every system, every corridor, every stored seed and every printed procedure exists to keep a population alive long enough to find out whether that estimate was any good. We will come back to the fact that the star is moving. It matters more at the end than it does at the beginning. Tau Ceti is the nearest single star that is genuinely like the Sun, and that sentence contains more qualifications than it appears to. There are closer stars. Almost all of them are red dwarfs, small, cool, dim, and prone to violent magnetic outbursts that would strip and sterilize anything orbiting close enough to be warm. The nearest system of all is a triple, which complicates every orbit inside it. Tau Ceti is neither. It is a single main sequence star of spectral class G8, one step down the scale from our own G2, and it sits in the constellation Cetus, faintly visible to the naked eye from a dark sky on Earth. It has been on every shortlist of interesting nearby stars for as long as such shortlists have been written down, and it has been the target of deliberate radio searching since the very first such searches were attempted. Nothing has ever been heard from it. Physically, it is a slightly smaller, slightly cooler version of the Sun. Its surface temperature is near 5,300 Kelvin, against the Sun's 5,770. Its mass is a little over 3/4 of the Sun's, its radius about 79%, and it radiates roughly half as much light. Those numbers matter for one practical reason. A dimmer star has a habitable zone that sits closer in. The band of orbital distances where liquid water could persist on the surface of a rocky world runs, on conservative definitions, from about 0.7 to about 1.3 times the Earth-Sun distance. Stretch the assumptions to the optimistic end, and the band widens to roughly 0.55 out to 1.32. Three further properties are what actually make Tau Ceti worth a 1,200-year commitment, and each of them is a genuinely good reason. The first is age. Estimates cluster somewhere between 8 and 10 billion years, which makes the star roughly twice as old as the Sun. Different methods disagree, as they usually do. Measurements based on the star's magnetic behavior suggest a younger figure, while measurements based on its internal oscillations and its measured size suggest an older one, and its chemical composition sits between them. All of them agree it is old. An old main sequence star is a settled one. It has finished whatever adjustments it was going to make, and it will go on producing very nearly the same amount of light for billions of years more. Over the 12 centuries of a crossing, its output is a constant, And being able to assume that is not a small thing when the entire mission is an assumption about a place nobody has visited. The second is quiet. Tau Ceti is remarkably inactive. It shows very few star spots, almost no variation in brightness as it rotates, and none of the flaring that dominates the behavior of the closer red dwarfs. A world in its habitable zone would not be periodically scoured by outbursts from its own star. This is the single largest question mark hanging over every nearer alternative, and Tau Ceti simply does not have it. The star is so steady that astronomers have used it as a reference standard against which to check their instruments, which is part of why its properties are unusually well measured for a star of its type. The third is that it is alone. No stellar companion, no complicating second gravity well, no orbits perturbed by another sun. Planets around a single star follow the simple paths that planets are supposed to follow. Against all of that sits one property that is not an advantage, and it should be stated in the same breath. Tau Ceti is metal poor. Its iron content is about a third of the Sun's. In the language of astronomy, everything heavier than helium is a metal, and a star's metal content records how many previous generations of stars had lived and died in the gas that formed it. Tau Ceti formed early, from material that had been enriched by fewer of them. That has consequences downstream, because planets are built from the same material as the star they orbit, and a system short of heavy elements is a system short of the iron and nickel and silicon that rocky worlds are made of. There is a further wrinkle in the chemistry that is worth noting quietly, because it changes what the planets there would be made of. The proportions of the elements in Tau Ceti are not simply a scaled-down copy of the Sun's. The ratio of magnesium to silicon in its light is measurably higher than ours. If the planets inherited that ratio, and planets generally do inherit the composition of the gas they condensed from, their rocks would be built around different minerals than the ones under our feet. That has knock-on effects that reach a long way, into how easily a planet's interior convects, into whether it has plate tectonics, and therefore into whether it has the slow geological cycle that keeps a climate stable over billions of years. None of this is known for Tau Ceti's worlds. All of it is implied by the star's own light, which brings us to what is actually orbiting there and to the honest state of the evidence. Tau Ceti has been watched for decades by instruments that measure the tiny back-and-forth motion a star makes as unseen planets tug on it. 4 periodic signals have been identified in that motion, with cycles of about 20 days, about 49 days, about 160 days, and about 642 days. All 4 imply worlds of modest size, minimum masses between roughly 1 3/4 and 4 times the mass of the Earth. And the 2 outermost signals sit near the inner and outer edges of the optimistic habitable zone, which is a genuinely interesting place for a pair of planets to be, and considerably less than a promise. We will come back to how much of this is known and how much is inferred. And then there is the dust. Submillimeter imaging revealed something around Tau Ceti that our own solar system has only a thin version of, a cold disk of dust surrounding the star, seen almost exactly face-on. Later observations at millimeter wavelengths resolved it properly. It is a broad belt with an inner edge somewhere around 6 times the Earth-Sun distance, and emission extending out to roughly 44, with earlier work suggesting material as far as 55. The total mass of dust in it is estimated at around 1 Earth mass. Dust of that kind does not last. Small grains are steadily removed by the star's own light, and by collisions, on timescales far shorter than the age of the system, which means a disk that is still there after 8 or 10 billion years is being continuously resupplied. Something is making it. The something is collisions between larger bodies, comets and asteroids grinding against each other, throwing off debris that we can see because it glows in the cold. The brightness of the disk is therefore a measurement of the population producing it, and the figure that comes out of that measurement is striking. Tau Ceti holds more than 10 times the cometary and asteroidal material of the solar system. The shape of the belt is worth a sentence of its own, because it is not the tidy ring that the word disk suggests. The observations constrain its width relative to its own radius, and that ratio comes out large. The belt is at least 3/4 as wide as it is far from the star. It is a broad, diffuse zone, rather than a narrow band, spread across tens of times the Earth-Sun distance, and there is no sharp outer edge to it in the data. Because it lies almost exactly face-on to us, we see it from above, as a pale ring of cold glow around a bright point, rather than edge-on as a line. That geometry is a piece of luck for imaging it, and, as we will see, a considerable inconvenience for almost everything else. For a mission planner, the number is very good news, and it is worth understanding why. A system rich in small bodies is a system rich in water, carbon, nitrogen, and metal, all of it sitting in gravity wells, so shallow that a spacecraft can arrive at one, take what it needs, and leave without spending anything worth mentioning. A civilization arriving at a star with 10 times our supply of comets does not have to land on a planet to survive. It has to reach out and take what is already loose. Tau Ceti, in other words, is an old, calm, stable, single, sun-like star with a habitable zone in a sensible place, a handful of small planet candidates, and an enormous accessible reservoir of raw material. There are reasons the shortlist has always had it near the top. We will come back to the disk as well. Departure is not a moment. It is a phase, and it has its own generation. Reaching 3,000 kilometers per second is not something that happens in an afternoon. At a very gentle acceleration, 1/10 of a meter per second squared, about 1/100th of Earth's gravity, an effect so slight that nobody aboard would notice it as weight. The burn takes about a year. Reduce the acceleration by a factor of 100, which many propulsion concepts require, and the burn takes a century. The propulsion phase of an interstellar mission is therefore not a launch in any familiar sense. It is a period of the voyage with its own routines, its own maintenance schedule, its own births and deaths, and its own particular set of ways to go wrong. During that burn, the ship has 2 different accelerations acting on it at once, and they do not point in the same direction. There is the thrust along the ship's axis, pushing it forward. And there is the spin of the rotating section, which manufactures the apparent gravity that keeps bones and muscles loaded. Those two add together the way any two forces add, which means the direction that feels like down inside the habitat is not the direction the floor was built for. It is tilted. Every floor in the ship is very slightly on a slope. Water sits at an angle in a glass, and a dropped object lands a little off from where it was released. When the engines finally shut down, that tilt slowly rights itself over the course of days, and the world inside settles into the shape it will hold for the next 12 centuries. Nobody who was alive when the engines lit will be alive to see them light again. Somewhere in the middle of all this, an event occurs that has no equivalent anywhere in human experience. The last supply vessel arrives, transfers what it is carrying, and departs. After that, there is nothing behind the ship. Not a delayed shipment, not a difficult resupply, not a long wait, nothing, permanently, for 1,200 years. Everything the ship will ever have is aboard it at that moment. Every atom of nitrogen, every gram of phosphorus, every spare bearing, every seed, every gene in every stored sample. From that afternoon onward, the inventory only ever gets smaller in the places where it cannot be recycled, and the entire discipline of the voyage consists of keeping that list of places short. The most unforgiving line on the manifest is the propellant. Delta V, the capacity to change velocity, is not like money, because it cannot be earned and it cannot be borrowed. The propellant reserved for braking at Tau Ceti is reserved permanently. It cannot be spent on a course correction without shortening the arrival, and it cannot be spent on an emergency without cancelling the mission. A generation ship therefore carries for 12 centuries an enormous quantity of something it is forbidden to touch, guarded by people who will never see it used. Everything else aboard has a similar quality, once you look at it properly. Stored food is not a supply of meals. It is a count of how many harvests the ship can afford to lose. Spare parts are not spares. They are a measure of how many times a given system may fail before somebody has to invent a repair from first principles. A reserve of anything on a 1,200-year voyage is simply a number of survivable accidents, and every accident that happens reduces it by one. There is a point during that first year at which returning becomes more expensive than continuing, and it arrives much earlier than intuition suggests. Turning back does not mean simply stopping. It means cancelling the entire velocity already gained, and then building it up again in the opposite direction, and then cancelling that too in order to arrive home at rest. 4 separate expenditures, where continuing requires only the one that was always budgeted. Long before the ship has left the sun's neighborhood, the cheapest available option is to keep going, and it stays the cheapest option for the rest of the voyage. Every decision made aboard for the next 12 centuries is made against that background. There is never a moment when going on is not the economical choice. The first generation carries a burden the others do not. They are the only people aboard who chose to be there, and they are the only people aboard who remember somewhere else. They are also the only ones who will ever have to explain the decision to somebody who did not make it. Whatever they build in those first decades, the customs, the schooling, the way the ship talks about itself, becomes the inherited ordinary for everyone who follows. Their descendants will not experience any of it as a choice. It will simply be how things are, in the same way that gravity and daylight are how things are for a person born on a planet. The other thing that ends during the first year is conversation. At departure, a message to Earth is answered promptly. Within weeks, the delay is measured in hours. Within a year, the round trip is longer than anyone's patience, and it keeps growing at the rate of 2 years of delay for every year of travel. There is no moment when communication is lost. It simply stretches, continuously, until the idea of asking a question and receiving an answer stops making sense. The people aboard the ship become autonomous, not by policy, but by physics, and the transition happens so gradually that no one can point to the day it was complete. Seen from outside, meanwhile, the ship is nearly invisible, and the one thing that gives it away is heat. 10,000 people generate about a megawatt of body warmth simply by existing, and the farms and the machinery generate a great deal more, and all of it has to go somewhere. In vacuum, there is no air to carry it away, so the only route out is radiation. The ship therefore carries enormous panels, whose entire purpose is to glow gently in the infrared, and those panels are by far its largest visible feature and its clearest signature. A living generation ship is a warm object in a cold sky. A dead one cools to the temperature of the space around it within weeks, and after that there is nothing to see at all. There is one more feature of the first year that is easy to miss. The ship is at its most fragile precisely when it is at its heaviest. At departure, most of its mass is propellant. Its structures are loaded, its engines are running, its systems are new and therefore unproven, and its crew consists entirely of people who trained on the ground for a vehicle that has never been operated. Every subsequent century is, in engineering terms, gentler than the first year. The coast is when the ship is at rest with itself. And there is a moment, somewhere out past the orbit of Neptune, when the ship crosses the boundary where the sun's outward wind of particles finally gives way to the gas between the stars. That frontier lies somewhere around 120 times the Earth-Sun distance. Our fastest existing machines took decades to reach it. A ship traveling at 1% of light speed crosses it within about 3 weeks of reaching cruise, and there is nothing to see when it happens. The boundary is detected as a change in the density of a plasma. It looks like nothing. It sounds like nothing. It is a number on an instrument that shifts and then holds its new value forever. Even that is not really leaving. Beyond it, the sun's gravitational domain continues, an enormous, sparse cloud of icy bodies that may extend a substantial fraction of a light-year outward in every direction. The ship spends decades inside it and encounters nothing because the objects in it are separated by distances that make the space between the planets look crowded. There is no gate. There is no threshold. There is only a slow thinning of everything, until one day the sun is simply the brightest star in the sky rather than the sky's source of light, and some while after that it is only the brightest star, and then, eventually, not even that. The supply line has ended. The engines have gone quiet. The floors have leveled. And the ship, carrying a population that will replace itself about 40 times before anything else happens, begins the part of the voyage that lasts for 1,200 years and contains almost no events at all. The space the ship is crossing is emptier than anything human beings have ever manufactured. The local interstellar medium holds roughly 3/10 of a particle per cubic centimeter. Mostly hydrogen, some helium, a scattering of everything else. To put that beside something familiar, the air at sea level holds about 25 billion particles in the same volume. The best vacuum ever produced in a laboratory, using every technique available, holds something like 10,000. Interstellar space is emptier than the emptiest thing we know how to make, by a factor of tens of thousands, and it maintains that emptiness across light years without any effort at all. About 1% of the medium's mass is not gas, but dust, solid grains, ranging from a few nanometers across up to about 1/4 of a micron. They are distributed along a steep curve, which means that for every grain of a given size, there are enormously more grains a little smaller. Large particles are correspondingly rare. The ship will meet uncountable numbers of the tiny ones, and, across 12 light-years, only a modest number of the ones big enough to matter. Here is where the choice of 1% of light speed quietly pays for itself, and it is the most underappreciated fact about slow interstellar travel. Everything the medium can do to a ship is kinetic. It is not chemistry, and it is not weather. It is objects arriving with a certain amount of energy, and that energy scales with the square of the speed. Double the speed and you quadruple the damage. So the medium is not a fixed hazard that every interstellar ship faces equally. It is a hazard whose severity is set entirely by how fast you decided to go. Take a single hydrogen nucleus striking the hull. At 3,000 kilometers per second, it arrives carrying about 47,000 electron volts. That is enough to knock atoms loose from the surface, and over centuries it produces a slow, sputtering erosion of whatever faces forward. It is not enough to penetrate the structure, and it is not enough to set off the cascade of secondary particles that turns fast interstellar flight into a radiation problem. Now, take the same nucleus at 10% of light speed. It arrives with 100 times the energy, in the millions of electron volts, and at that point, the ship is no longer flying through a thin gas. It is flying into a particle beam that it is generating itself, simply by moving, and the faster it goes, the harder that beam becomes. There is a real threshold in there, and 1% of light speed is comfortably below it. The same arithmetic applies to dust. A grain weighing 10 micrograms, a speck, invisible, less than a grain of salt, striking at 3,000 kilometers per second, delivers about 45 kilojoules. That is roughly the energy of 10 grams of high explosive going off against the hull. It is a serious impact, and a survivable one, and encounters at that scale are rare. The same grain at 10% of light speed delivers about 4.5 megajoules, which is a different category of event entirely, and the difference between the two is nothing but speed. Protecting against the impacts that do occur uses a technique that is old, well-proven, and almost elegantly simple. A thin sacrificial sheet is mounted some distance in front of the real hull. An incoming particle strikes the sheet and, because the impact energy vastly exceeds what is needed to vaporize it, does not punch through so much as explode. What continues onward is not a bullet, but a spreading cloud of vapor and fragments, which arrives at the actual hull, spread across a wide area and carrying the same total energy at a survivable intensity. Spacecraft in Earth orbit have used this method for decades against orbital debris. It scales, it needs no power, and it fails gracefully. The erosion is worth quantifying because it is the one continuous guaranteed form of damage the crossing inflicts. A ship traveling at a substantial fraction of light speed loses something on the order of 0.5 millimeter from its forward-facing surfaces over a crossing of a few light years. At 1% of light speed, the figure is very much smaller, and it accumulates over 12 centuries rather than a few. The forward hull does not fail. It thins, imperceptibly, for the entire mission, and the thinning is the most reliable clock aboard, a measurement that can be taken at any time and that only ever moves in one direction. The medium itself is not uniform either. The Sun currently sits inside a particular cloud of interstellar gas, and beyond it lie others, with densities that differ from one another by factors of a few. Somewhere in the 12 light-years to Tau Ceti, the ship almost certainly passes from one into the next. Nothing dramatic marks the transition. The erosion rate changes slightly, the particle count on an instrument shifts, and the crossing continues. There are also magnetic fields threading the whole region, measured in a few millionths of the strength of Earth's, which are far too weak to matter to a coasting ship, and which become interesting again only at the very end, when something is needed to push against. One last curiosity about the medium is that it is, technically, hot. Parts of it sit at thousands of degrees, in the sense that the individual particles are moving very fast. That fact has almost no practical meaning, because temperature and heat are different things, and with 0.3 of a particle per cubic centimeter, there is simply nothing there to transfer warmth. A ship in interstellar space is not heated by its surroundings, and is not cooled by them either. It is thermally alone, and every joule it produces has to be deliberately thrown away. What the ship cannot shield against by being slow is the radiation that was already out there. Galactic cosmic rays do not care how fast the ship is going. They are atomic nuclei accelerated to enormous energies elsewhere in the galaxy, arriving from all directions, and they deliver roughly 1.8 millisieverts of dose per day to anything unprotected in deep space. That figure holds for the entire 1200 years. It is the dominant radiation term of the mission, and it is completely indifferent to every design choice except one, which is how much mass sits between the crew and the outside. and mass is the only answer, which produces one of the more counterintuitive facts in spaceflight engineering. A partial shield can be worse than no shield at all. A very high-energy nucleus striking a thin barrier does not stop. It shatters, and the fragments are themselves energetic particles, and a shower of them emerges from the far side that can be more damaging than the single particle that went in. Shielding, therefore, has to be thick enough to absorb the whole cascade, or it should not be there. Materials rich in hydrogen do this far better per kilogram than metals do, because a proton stops a proton more efficiently than a heavy nucleus does, which is why water and hydrogen-rich plastics appear in every serious design. It is also why the ship's own water supply tends to be drawn on the plans as a shell wrapped around the places where people sleep. The water has to be somewhere. It might as well be somewhere useful. There is one final property of deep space that runs against expectation, and it is worth ending on, because it shapes the next 1,000 years. Deep space is the finest preservative there is. There is no oxygen to oxidize anything, no water to corrode it, no biology to consume it, no gravitational load to creep under, and none of the daily temperature cycling that fatigues materials on a planet. Metal left out there does not rust. Structures do not sag. A spacecraft parked in interstellar space is in a chemically gentler environment than any warehouse on Earth. The consequence for the mission is a strange one. The environment outside is doing almost nothing to the ship. The erosion is slow, the impacts are rare, the radiation is steady and answerable with mass, and the chemistry is inert. If the ship were empty, it could cross to Ceti and arrive in almost the condition it left. The overwhelming majority of everything that can go wrong on this voyage originates inside the hull, in the machinery and the ecology and the people, and not outside it. Things do not rot out there. They wear out. That is a different problem, and it belongs entirely to the people aboard. The vehicle that actually has to survive 1,200 years is not the hull. It is the loop. Every closed habitat rests on 4 numbers, and they scale in a straightforwardly linear way, which makes them unusually easy to plan around. A person consumes about 0.84 kilograms of oxygen a day. A person produces roughly a kilogram of carbon dioxide. A person needs somewhere between 20 and 40 kilograms of water a day for everything: drinking, washing, cooking, cleaning. And a person radiates about 100 watts of heat continuously, which is a small electric heater running in every body aboard, all the time, whether asleep or awake. Feeding one person requires between 20 and 40 square meters of intensively cultivated growing area, depending on what crops are chosen, how brightly they are lit, and how much variety in the diet is considered acceptable rather than luxurious. Multiply by 10,000 people, and the ship acquires its real dimensions. 8 tons of oxygen consumed a day. 10 tons of carbon dioxide produced. A megawatt of body heat. Something like 50 acres of farm, lit artificially, running continuously, forever. The good news is that the machinery to do most of this already exists and has been running for decades. Water is recovered from every available source: condensate from the air, wastewater, humidity from the crops, at about 90% efficiency in routine operation, with 98% achieved under test conditions. Carbon dioxide is scrubbed from the air and then, through a well-established catalytic reaction with hydrogen, converted back into water and methane. The water is electrolyzed to release oxygen. The methane is thrown overboard. It is a genuinely impressive piece of engineering, and it has kept people alive continuously for a very long time. It is also not closed. It leaks. It consumes filters and catalyst beds and seals. It is resupplied several times a year, and the resupply is not incidental to it. It is part of how it works. A generation ship has to run the same functions with no resupply at all for 12 centuries, and that is not a harder version of the same problem. It is a different problem wearing the same name. The elements that cause trouble are not the ones people expect. Oxygen and carbon cycle readily because they exist in gaseous forms that a machine can catch. Nitrogen is required in enormous quantities and does almost nothing chemically. It is there to make up the pressure and to keep the fire risk manageable, but every time an airlock cycles, some of it is lost, and there is no way to make more. Phosphorus is worse, and it is the element that quietly disappears in every closed loop ever built. It is essential to life, and it has no gaseous phase. It binds into sludge at the bottom of tanks, into scale on the inside of pipes, into biomass that gets composted imperfectly or discarded. Each individual loss is negligible. Over 1,200 years and 40 generations, the losses are the mission. A ship that runs out of phosphorus does not have a crisis. It has a farm that gradually produces less, for reasons that take a long time to identify. The farm deserves more attention than it usually receives, because it is not a garden attached to the ship. It is an organ of the air system that happens to produce food as a byproduct. Crops need roughly 1,000 watts of light per square meter to grow properly, against about 200 for a comfortable living space. That makes the farm the largest single consumer of power aboard, and by extension, the ship's furnace. Every watt that goes into it comes back out as heat that the radiators have to shed. The thermal system, not the food supply, is what actually limits how much can be grown. Farms also move enormous quantities of water. Plants transpire continuously, and every drop they release into the air has to be caught and returned. The largest water handling machines aboard are therefore not pumps, but condensers, quietly pulling the farm's own breath back out of the atmosphere. A great deal of the ship's plumbing exists to undo what the crops do. And a farm in a sealed world has to be managed in ways that a field never does. There is no wind and no dependable insect population, so pollination is a scheduled task performed deliberately. Planting is staggered rather than seasonal, so that a disease sweeping through one crop does not take the entire harvest at once. A firebreak made of calendar rather than distance. Growing in soil carries a microbial community that sterile hydroponic systems do not, and there is a serious argument that this matters for human health rather than just for the plants. Immune regulation appears to depend on continuous exposure to a rich environmental community of microbes, and indoor environments are measurably impoverished in exactly that respect. A very clean ship may be a subtly unhealthy one over generations. Even the diet is an engineering quantity. Variety costs area, because the crops that provide it are usually less efficient than the ones that simply provide calories. Every additional flavor on the table is measured in square meters of farm and kilowatts of light, and a society that decides monotony is unacceptable has decided to build a larger ship. Which brings us to the most instructive thing anyone has ever learned about sealed ecosystems, and it did not happen in space. A large sealed enclosure on Earth, containing a crew, farmland, and several manufactured ecosystems, was run continuously for about 2 years. Over roughly the first 15 months, the oxygen concentration inside fell steadily from the normal 21% down to around 14%. That is the equivalent of being moved, without warning, to an altitude of several thousand meters, inside a sealed building at sea level, and the people inside became measurably impaired before anyone understood why. The cause turned out not to be a leak, and not to be the crops, and not to be anything anyone had modeled. It was the concrete. The structure contained a great deal of it, uncured, and uncured concrete absorbs carbon dioxide out of the air. That single, unaccounted-for process broke the expected balance between what the plants took in and what the people breathed out. Oxygen was being consumed by soil microbes at a normal rate, but the carbon dioxide that should have appeared in exchange was disappearing into the walls. Everyone was watching the carbon dioxide, because carbon dioxide is the thing you watch. The oxygen fell at about 140 parts per million per day, and the metric that would have revealed it was not the metric anyone had chosen. That is the lesson, and it generalizes perfectly to a ship. A closed system is not usually killed by a dramatic failure. It is killed by a slow process that nobody put in the model, running in a direction nobody is measuring, hidden behind a quantity that looks reassuring. Which means that monitoring aboard a generation ship is not a support activity. It is the primary activity. The dangerous failures are precisely the ones with no alarm attached, because an alarm can only exist for a failure somebody anticipated, and 1200 years is long enough for the unanticipated to be a statistical certainty rather than a possibility. A crew's real work is not fixing things. It is noticing them. Separately, a long-running program of sealed ecology experiments achieved high degrees of closure across 10 successive runs, with crews growing much of their own food and recycling most of their own air and water. The longest of those closures lasted about 180 days. 6 months. That is the record. Not for a comfortable closure, but for any closure at all. It is worth stating plainly that no closed ecological system has ever been operated for a decade, let alone a century, let alone 12 of them. The gap between what has been demonstrated and what a generation ship requires is not a matter of refinement. It is a factor of more than 2,000, and no amount of careful design substitutes for evidence that does not exist. A ship departing for Ceti is not relying on proven technology. It is relying on an extrapolation, and the honest description of the voyage includes that sentence. There are arguments on the other side, and they are real. A larger system is more stable than a small one, and every closure attempted so far has been tiny. Buffer volume is measured in days. A habitat with a great deal of atmosphere has a long time between a failure and a fatality, and that time is where all the repairs happen. Scale is not a luxury on a ship like this. It is the single most effective safety measure available, and it is the strongest argument in the entire discipline for building something enormous rather than something efficient. The people aboard are not a crew. They are a population, and the difference becomes obvious the moment you count them properly. 1,200 years at roughly 30 years to a generation gives about 40 complete turnovers of everybody aboard. Count generations a little shorter, at 25 years, and the number rises to nearly 50. Either way, the ship replaces its entire human contents dozens of times before anything happens. Nobody who leaves arrives. Nobody who arrives chose to go. And in between sits the great middle of the voyage, call it years 200 through 900, in which there is no departure to remember, no arrival to anticipate, no external event of any kind, and no possibility of help. The question of how many people are needed has been studied more carefully than most aspects of interstellar travel, largely because it is one of the few that can be modeled with existing biology. The genetic flaw, the number required to avoid the accumulated harm of a population breeding within itself for dozens of generations, comes out in the several hundreds to low thousands, depending on how the founding population is selected and how carefully reproduction is managed. Design studies have proposed crews of around 1,000. Analyses that ask the harder question of what happens when a disease sweeps through and takes a large fraction of the population at once argue for numbers closer to 10,000, on the grounds that a ship should arrive with enough diversity left to be worth arriving with. But the genetic flaw is not the binding constraint, and this is the part that tends to be overlooked. The occupational flaw is higher. A ship needs people who can maintain a reactor, and people who can maintain the machines that maintain the reactor, and people who can teach both of those skills to the next generation, and enough of each so that an illness or an accident does not take the last person who knows something. Every skill aboard needs redundancy in the present and continuity into the future, and the number of distinct skills a self-repairing world requires is very large. Population is not set by biology. It is set by the length of the list of things that must never be forgotten. And things are forgotten. This is not speculation about the far future. It is a documented pattern in ordinary human institutions on ordinary timescales. Organizations lose the ability to do things they once did routinely, within a single working lifetime, even with continuous operation and complete documentation. Manufacturing techniques have been lost while the factories were still standing and the manuals were still on the shelf. The reason is always the same. Competence does not live in files. It lives in bodies. A complete written account of how to repair a component is not the same thing as a person who has repaired one, and the gap between the two is the central maintenance problem of a 12-century voyage. The archive is not the knowledge. The archive is a set of instructions for reconstructing knowledge, and reconstruction takes someone who already half knows. There is also a pattern in the psychology of long confinements that is directly relevant and slightly unsettling in its regularity. Studies of isolated crews, in polar stations, in sealed simulation facilities, in orbit, repeatedly find a trough of morale and motivation that arrives around the 3/4 mark of the confinement. It is consistent enough to have a name. What makes it interesting is that the trough appears to be largely independent of how long the confinement actually is. It arrives at 3/4 of the way through, whether that is 3/4 of a winter or 3/4 of a year and a half. A 520-day sealed isolation study, run with a small crew, found exactly that pattern along with a set of slow physiological drifts, activity declining, sleep timing shifting, light exposure gradually falling as people spent more of their time in the dimmer parts of the facility. And then, in the final weeks, a marked rebound. Activity rose, mood lifted, engagement returned. The end was in sight, and the sight of it did the work. That mechanism does not exist in the middle of a 1,200-year voyage. There is no approaching end for anyone born in the 3rd century. Their 3/4 mark is not the ship's 3/4 mark, and whatever they experience of confinement has to resolve some other way, or not resolve at all. It is one of the few places where the evidence from terrestrial isolation studies genuinely fails to transfer, and it fails in a direction nobody has data for. The body responds to long isolation in ways that are measurable and not obviously psychological. Crews on long-duration missions show reactivation of latent viruses at rates around 1 in 2, infections acquired decades earlier, dormant for a lifetime, quietly waking up. The pattern tracks stress hormones rather than any external exposure, which means the trigger is the situation rather than the environment. On a ship that has a peculiar consequence, there is no epidemiological outside. A pathogen aboard has nowhere to come from and nowhere to go. It either burns through the population and disappears, or it becomes a permanent resident of the ship, cycling through the generations indefinitely, part of the furniture. The interior itself does work on people that is easy to underestimate. Research on how environments restore attention identifies a set of conditions, a sense of being away, enough content to hold the mind, coherence, and a fit between the place and what a person wants to do there. A fully designed interior satisfies some of those conditions well, and one of them almost not at all. There is no away. Every space aboard was drawn by somebody, for a purpose, and there is no corner of the ship that is merely there. That is why serious habitat designs go to real trouble to create long sightlines, concealed districts, places that are not fully visible from anywhere else, and landscaping that hides the machinery rather than displaying it. Not for deception, for the ordinary human requirement of being somewhere that is not entirely accounted for. Over enough generations, the mission itself becomes a story rather than a plan. The people who decided to go, and their reasons, and the world they left, pass out of memory and into narrative, and narratives are subject to the ordinary distortions of anything handed down. The founding becomes an origin story. The destination becomes a promise. Whether that helps or hurts depends entirely on how the story is told, and nobody who wrote the mission plan has any influence over how it will be told in the year 900. There is one thing that would change all of this, and it is worth naming, because it is the only real solution anyone has proposed. Send more than one ship. A second vessel traveling alongside is the only genuine outside available, another society to compare against, another archive, another independent copy of every skill and every seed bank, and somewhere for a person to go who cannot stay where they are. A fleet is not a redundancy measure bolted onto a mission. It is a fundamentally different kind of voyage, and almost every problem in this part gets smaller when there are two. Meanwhile, the culture itself moves. Language drifts measurably over 40 generations, pronunciation first, then vocabulary, then the shape of sentences. Words survive their reference and become abstractions. Rain, horizon, coastline, weather, seasons, all of them stay in the language because they are in the archive and in the songs, and none of them describe anything anybody aboard has seen. The second generation speaks with an accent the first does not have. The 10th speaks something that would take the first a moment to follow. The 40th is speaking a related but distinct language, and the founding documents of the mission are, by then, historical texts requiring interpretation. And the ship carries an archive of a civilization that is, from the ship's point of view, receding at the speed of light, still transmitting, still arriving, always older than it looks. This is a good place to stop and gather up what the voyage has been so far, because the second half of it turns outward. The schedule and the speed are the same number. 1,200 years and 1% of light speed are two ways of writing the same decision. The destination is a specific star, old, calm, single, metal-poor, sun-like, with a habitable zone closer in than ours, 4 unconfirmed planet candidates, and an unusually rich belt of debris. Departure ended the supply line permanently and locked the propellant ledger, and returning stopped being the cheap option within the first year. The space in between is emptier than anything manufacturable, and at this modest speed, mostly leaves the ship alone. The loop inside, air, water, soil, crops, phosphorus, is the real vehicle, and its failures are slow, quiet, and hidden behind the wrong instruments. And the population is not a crew but a small civilization that will replace itself 40 times before anyone sees the far end. From here, the episode turns away from the inside of the ship, to the machine that has to keep working, to the sky outside, which almost nobody thinks about, to the message from home and what it costs, and to the place at the end of it, which is not what it appeared to be from 12 light years away. Halfway through the crossing, the ship has been coasting for 6 centuries and has covered 6 light-years. Nothing has struck it. Nothing has catastrophically failed. And it is, in a way that matters, no longer the same object that departed. Every component that could be replaced has been replaced some number of times. Every component that could not has aged. The hull is thinner on the forward face by an amount too small to see. The bearings have been rebuilt. The wiring has been rerun. The people who designed all of it have been dead for 20 generations, and the people maintaining it have never met anyone who was there when it was new. Start with power, because power is where the timescale bites first and hardest. Our long-duration spacecraft run on radioisotope sources, slugs of material that generate heat as they decay, converted directly to electricity with no moving parts. They are extraordinarily reliable, and they are completely useless here. The standard isotope has a half-life of about 88 years. Over 1,200 years, that is nearly 14 halvings, which means the output at arrival is roughly 1/13,000th of the output at departure. A power source that starts at a comfortable few hundred watts finishes at a fraction of a watt. Anything nuclear aboard a generation ship must be a fueled reactor that can be refueled and maintained, not a sealed cylinder that quietly runs down. That single fact excludes the entire class of power system that has served our deepest missions. Radiation does its slow work on the ship, as well as on the crew. The same 1.8 millisieverts a day that the people have to be shielded from is also accumulating in the materials. Glass develops color centers and slowly darkens. Crystalline solids accumulate displacement damage, where individual atoms are knocked out of their proper positions in the lattice. Neither effect meaningfully weakens structure over these timescales. Both degrade optics, sensors, and electronics, which are precisely the components a ship cannot do without and cannot easily rebuild. Metals, on the other hand, do remarkably well. In vacuum, there is nothing to corrode them. Structural steel and aluminium out there are in a chemically gentler environment than anything on a planet, and a hull left alone would remain sound and recognizable for something between 100 million and 1 billion years. If the only question were whether the ship's frame survives 12 centuries, the answer would be that 12 centuries is nothing. The materials that genuinely age are the soft ones, and they are in everything. Polymers, seals, gaskets, insulation, wire jackets, adhesives, flexible hoses, the coatings on almost every surface, embrittle under radiation and slowly outgas into vacuum. They lose their flexibility, then their sealing, then their integrity, in that order. There is no polymer in existence with a demonstrated 1,200-year service life, and they are used by the thousand in every pressurized structure ever built. If the ship has a true consumable, it is not fuel or food. It is the rubber. Then there is a failure mode that has no equivalent on the ground at all. In vacuum, 2 clean metal surfaces brought into contact can simply bond to one another because there is no oxide layer and no adsorbed gas between them to keep them apart. The atoms on each surface do not distinguish between their own solid and the other one. This is cold welding. It is a documented problem on real spacecraft, and it turns every external moving joint into a maintenance item on a schedule measured in decades. Hinges seize. Latches fuse. Mechanisms that have been left alone for a long time are the ones most likely to have become a single piece of metal. And underneath all of it, the rotating habitat turns. Whatever bearing carries that rotation has to run continuously, under load, for 1,200 years, and be serviceable by people working from drawings whose authors they cannot ask. That is not a materials problem, so much as an intent problem. Every design decision embeds assumptions the drawings do not record. The tolerance that was chosen for a reason, the clearance that exists because of something discovered during testing, the part that is oversized because of a failure nobody wrote down, all of it must survive as knowledge, not just as geometry, for 40 generations. The size of that bearing is set by arithmetic that has nothing to do with materials. Apparent gravity from rotation depends on the radius and on the square of the rotation rate, and the rotation rate is limited by human tolerance rather than by engineering. Turn faster than about 2 revolutions per minute, and people begin to notice the effects when they move their heads. Turn much faster than that, and a substantial fraction of them are unwell for weeks. To produce a full Earth gravity at 2 revolutions per minute, the habitat needs a radius of about 224 meters. To do it at 1 revolution per minute, comfortable for essentially anybody, it needs about 895. Those are the dimensions of the thing that has to keep turning smoothly for 12 centuries, and they are not small. That, in turn, reshapes what the ship's population actually spends its time doing. On any terrestrial vehicle, maintenance is what happens when something is wrong. Here it is the standing condition. A very large fraction of the working population is engaged, permanently, in inspecting things that are not broken in order to find the ones that are about to be. Inspection is the ship's real economy, and its currency is attention. A society that stops finding this work meaningful has a serious problem long before it has a mechanical one, and there is no external pressure to keep it interested. No deadline, no customer, no visible consequence for a job done adequately rather than well. Motivation is a structural component of the vehicle, and it has to be maintained on the same schedule as the bearings. There is even a problem with the calendar, which sounds trivial until it is examined. The ship needs to know what year it is, precisely, for 1,200 years, because navigation depends on it. Clocks drift. Records are copied and miscopied. The accumulated error in a hand-kept calendar over 40 generations can be substantial, and on Earth it has been, repeatedly, in societies with far better external references than a ship possesses. The ship has to keep time against something that does not depend on anybody remembering, which is another argument for navigating by the pulses of distant neutron stars, since those pulses are a clock nobody aboard can lose. The software has the same difficulty in a purer form. Code does not decay. It sits in storage, unchanged, indefinitely. What it loses is maintainability. The people who understood it die, and their students die, and the tools used to modify it are themselves software with the same problem. Worse, code encodes assumptions about the mission, about what the ship is doing, what state it is in, what year it is, and those assumptions stop matching reality long before anybody notices. A generation ship's control systems do not break down. They become progressively less well understood, until the point where nobody aboard can safely change them, and the ship is being flown by a set of decisions made 12 centuries earlier. Which raises the question of the archive itself, and it is a quieter crisis than it sounds. Everything the ship knows, every procedure, every schematic, every scientific result, every book, has to remain readable for 1,200 years. Magnetic media fail on timescales of years to decades. Optical discs are no better. Every storage technology in common use degrades faster than a single human lifetime, and the standard answer on Earth is continuous migration. Copy everything for new media, forever, and never stop. That works as long as the institution doing the copying survives, which on a ship is exactly the thing in question. Storage etched physically into fused quartz has been demonstrated, with projected lifetimes far beyond anything else available, and something of that character is required, for anything the ship must still be able to read in year 1000. It is worth being fair about what has actually been achieved, because the record is genuinely impressive. Spacecraft thrusters unused for 37 years have been commanded to fire and have fired. Instruments have operated after absorbing 4 times their design radiation dose. Machines built with the technology of half a century ago are still returning data from beyond the edge of the sun's influence. Hardware longevity in deep space is real and demonstrated. It is demonstrated for about half a century. The ship needs 1200 years, which is a factor of about 25 beyond anything our species has ever operated. That gap is not filled by better engineering. It is filled by the ability to manufacture aboard, to make new parts from raw material, rather than draw them from a store that would, if sized for 12 centuries, weigh more than the ship. Manufacturing requires furnaces, and furnaces require power, and power requires radiators, which is how the thermal system ends up quietly setting the limit on how much industry a generation ship can support. And every repair consumes something. A little metal, a little sealant, a little of somebody's remaining life. Over 1200 years, the total consumed is a real number, and no design study has ever credibly produced it. There is one thing this voyage produces that nothing else ever has, and it is not at the destination. It is halfway. 6 light-years from the Sun and 6 from Ceti, the ship occupies a vantage point no instrument of ours has ever occupied. Our furthest machines are about 1/5 of a thousandth of that distance out. From the middle of the crossing, for the first time, the sky is genuinely different. Not different in the sense of being a little clearer, but different in its arrangement. The reason is parallax, working on a scale it has never worked on before. When a viewpoint shifts sideways, nearby objects appear to move against distant ones, and the amount they move depends on how close they are. From Earth, the largest baseline available is the width of our orbit, and even that is enough to measure the distances to thousands of stars by watching them shuffle very slightly over the course of a year. Move the viewpoint 6 light-years and the effect becomes overwhelming. The nearest stars swing across enormous arcs. The far ones barely stir. So the constellations come apart, but not evenly, and not in a way that looks like a shuffle. Each pattern in Earth's sky is an accident, a set of stars at wildly different distances that happen to line up when viewed from one particular place. Move that place, and each pattern deforms in proportion to which of its stars are close by. A constellation made entirely of remote, luminous giants survives the journey almost untouched, because a few light-years is nothing to something 1,000 light-years away. A constellation containing one nearby star has that star pulled out of formation and dropped somewhere else in the sky, and the shape is simply gone. The Milky Way itself does not change at all. Its band across the sky is a structural feature of a galaxy 30,000 light-years across, and 6 light-years is not enough to alter it in any perceptible way. Whatever else the ship's sky looks like, the same faint river runs through it, in the same place, for the whole of the 1200 years. And what of the 2 stars that matter? The Sun, seen from the halfway point, is about a first-magnitude star. That is genuinely bright, comparable to the brightest stars in Earth's night sky. It is also entirely ordinary-looking. There is no mark on it. Nothing distinguishes it from its neighbors, and a person aboard who did not know where to look would never find it. Everything that has ever happened to our species happened around that unremarkable point of light, and from 6 light-years away, there is no way to tell. Ceti, from the same place is roughly 1 magnitude fainter. Second magnitude. Also ordinary, also unremarkable, also indistinguishable from any number of other stars in the same direction. For a long stretch of the middle voyage, the origin and the destination hang on opposite sides of the sky as two bright and unimpressive dots, and neither of them looks like anything in particular. Some stars survive the move better than others, and which ones do is entirely a matter of distance rather than of brightness. The brightest star in Earth's sky is bright partly because it is genuinely luminous, and mostly because it is close, a little under 9 light-years away. From the halfway point it would be substantially displaced and noticeably changed in brightness, because 6 light-years is a large fraction of its distance. Meanwhile, the great luminous stars that anchor the winter sky are hundreds or thousands of light-years off, and they would sit almost exactly where they have always sat, unmoved and unbothered. The practical consequence is that navigating by the look of the sky stops working. Star patterns are a local convenience, not a fixed reference, and any method that depends on recognizing shapes fails the moment the viewpoint moves far enough to matter. What continues to work is navigation by absolute position, timing the pulses of distant rotating neutron stars, which keep their rhythm regardless of where they are observed from, and which are far enough away that the ship's motion barely touches them. That is a second reason those objects appear in every interstellar design study. They are the only landmarks in the galaxy that do not move when you do. There is also a question of whether anyone is looking out at all. A window is a hole in the shielding, and shielding is the ship's principal defense against a radiation environment that never lets up. Any direct view of the sky costs something, and on a well-designed vessel, it is likely to be a small, heavily protected, deliberately provided facility rather than a feature of ordinary rooms. Most people aboard would see the outside the way most people on Earth see the deep ocean floor, through instruments, on a screen, faithfully and at second hand. The sky is available. It is simply not casually available, and over 40 generations that distinction shapes how much the outside figures in anybody's daily thinking. Seen from outside, the ship itself would be effectively invisible. It emits almost no light of its own. It reflects nothing, because there is nothing to reflect, and the only thing that would give it away at any distance is the infrared glow of its radiators. Even that is a faint, warm patch against a very cold background, and it would take a deliberate search by somebody who already suspected something was there. 1,200 years of travel, 40 generations of people, an entire self-contained world, and from a light-year away, nothing. There is one genuine optical effect of the ship's speed, and it is a small one. Light arriving from ahead is slightly tilted by the ship's motion, in the same way that rain falling straight down appears to slant when you walk through it. The size of the shift is set by the ratio of the ship's speed to the speed of light, 1%, which works out to a little over half a degree. Every star in the sky is displaced by about that much, toward the direction of travel. It is slightly more than the apparent width of the full moon. It is permanent for as long as the ship coasts, and it is invisible to anyone who does not have a chart to compare against. Relativity does nothing else worth mentioning. At 1% of light speed, time aboard runs slow relative to Earth by about 1 part in 20,000. Over the entire 1,200 years, the ship's clocks fall behind by roughly 3 weeks. Nobody is saved any time. Nobody arrives younger in any meaningful sense. The dramatic effects of relativistic flight belong to speeds this ship will never approach, and the crossing is exactly as long for the people making it as it is for anybody watching. Which leaves the strangest feature of the view, which is that it does not move. Everything visible from the ship is light-years away. At 1% of light speed, Covering a light year takes a century, which means the entire visible universe changes at a rate of 1 century per unit of noticeable difference. There is no landscape going past. There is no sense of travel. A person could stand at a window for their whole life and see nothing shift at all, and their grandchildren would see almost the same sky. The ship is moving faster than any object our species has ever built, through a galaxy, toward a star, and from the inside there is no evidence of motion whatsoever. It is worth saying what could actually be done from that vantage point, because the scientific value is not small and it does not depend on arriving anywhere. A parallax baseline of 6 light-years is more than 350,000 times wider than the one available from Earth. Distances that are currently measured with difficulty and considerable uncertainty become straightforward. Stars whose distances are known only approximately could be pinned down precisely. The three-dimensional structure of the entire local region of the galaxy could be mapped to an accuracy that is simply not available from a single point. The ship is the only observatory our species would ever have with a baseline measured in light-years. Whatever else the voyage does or fails to do, that instrument exists for the entire 1,200 years, and it is pointed at everything. And the light itself arrives very slightly reddened over these distances by the thin dust the ship has been passing through, a change so small it takes an instrument to detect it, and a reminder that the emptiness is not quite empty after all. Tau Ceti is 11.9 light-years away. That number was introduced at the beginning of this journey as a distance. Here it comes back, entirely unchanged, and means something completely different. 11.9 is not only how far the destination is. It is the price, in years, of every question the ship might ever ask of home. A message leaving Earth reaches Tau Ceti 11.9 years later. A question asked and answered costs 23.8. Nobody aboard this ship ever has a conversation with anybody outside it. What they have instead is correspondence with a civilization that has already moved on by the time each letter lands, conducted at a pace where a single exchange takes longer than a career. The delay does not arrive all at once, which is part of what makes it strange. It grows continuously, in step with the distance. In the first year, it is a matter of days. By the 1st century, it is a year. At the midpoint, it is about 6 years, so that a message sent by a person in their 20s is answered when they are in their 40s, and only if somebody at the far end thought the question worth replying to. By the final century, the delay is over 11 years and still climbing, and the ship is asking questions of a world that has aged 1,200 years since anybody aboard had ancestors living in it. One consequence is worth pausing on, because it inverts something people take for granted. On Earth, distance and difficulty of communication have always been roughly the same problem, and both have always been solvable by trying harder. Here they separate completely. The channel to home never degrades in quality. A signal that arrives clearly. What degrades is only its age. The ship is never cut off. It is simply always talking to the past, and the past keeps getting further away at a fixed and perfectly predictable rate. There is no rescue at any point in this. That is not a matter of policy or funding or will. It is a matter of geometry. Even if something went wrong in the first decade and every resource on Earth were turned toward helping, the help would arrive after the crossing was over. Autonomy aboard a generation ship is not a design philosophy. It is a physical property of the situation, and it applies from very early on. The engineering of the link is its own difficulty. Received signal power falls with the square of distance, and the distances here are absurd. Our deep space probes, at a few tens of times the Earth-Sun distance, already work at data rates measured in tens of bits per second, using antennas tens of meters across at the receiving end and every trick in the discipline. At 11.9 light-years, the numbers become something else again. Closing the link requires an enormous fixed installation at the Earth end, transmitting a great deal of power at a very narrow beam, aimed at a moving target across more than a decade of light travel. It is not a two-way channel in any practical sense. It is a broadcast, a large, permanent thing talking to a small, distant one, which can reply only slowly, faintly, and at length. And the ship must aim its own receiver at where Earth will be, not where Earth appears. The same problem it has with its destination, running in the opposite direction and requiring the same kind of prediction. The pointing accuracy needed for a laser link, which is far more efficient than radio at these distances, is a maintenance discipline in its own right, sustained across centuries by people who cannot verify that it is working. The traffic in the other direction has a peculiar quality of its own. Everything the ship sends home is a historical document by the time it is read. A report of a failure describes a crisis that was resolved, one way or the other, more than a decade before anyone on Earth learned of it. A request for advice is answered on the assumption that the situation still exists, and it may not. The most unsettling case is the routine one, a ship transmitting steadily that all is well, with the understanding on both sides that the message proves only that all was well, a long time ago, and proves nothing at all about now. The ship is always sending news of a past version of itself into a future version of home. What comes down that narrow channel, though, is the most valuable cargo the ship receives after the last supply vessel departs. It is information about the destination. Consider what is actually known about Tau Ceti's planets at the moment of launch. 4 periodic signals in the star's motion. Minimum masses. Orbital periods. That is very nearly the whole of it. No radii, no densities, no compositions, no atmospheres, no images. Everything the mission is founded on comes from watching a star wobble by a few meters per second, which is a genuinely extraordinary measurement and answers almost none of the questions a settler would want answered. Now consider what 1,200 years of astronomy at home would do to that picture. Instruments the launch generation never imagined, operating from platforms that do not yet exist, watching the same star for over a millennium. Sizes measured. Compositions constrained. Atmospheres detected, if there are any. Possibly images, actual resolved light from actual worlds. All of it beamed outward, into the dark, toward a ship that is already most of the way there. So the ship learns what it is flying toward while flying toward it. The generation that arrives knows enormously more about the destination than the generation that chose it, and every piece of that knowledge came from behind them, arriving at the speed of light and overtaking them at 99 times their own pace. Every update is 11.9 years old when it lands. And it describes a system being observed from 11.9 light-years away, which is to say that even the newest information about Tau Ceti, at the moment it reaches the ship, is describing the star as it was some 24 years before the ship read the message. There is a scenario in that arrangement that deserves to be named because it is entirely plausible and there is no good answer to it. Suppose that 2 centuries into the crossing, a message arrives explaining that better observations have shown the destination to be considerably less promising than everyone believed at launch. The habitable zone candidates turn out to be too massive, or airless, or shrouded, or simply absent, signals that dissolved under better scrutiny, as candidate planets sometimes do. The ship receives this. And then the ship continues, because there is nothing else it can do. Its propellant is committed, Its trajectory is set, and the nearest alternative star is a fresh voyage of comparable length that it does not have the resources to begin. Bad news travels at the speed of light and arrives with no accompanying options. The mirror image is equally plausible and considerably kinder. A message might arrive announcing that one of the candidates has an atmosphere, or water, or something more interesting still. That news travels at exactly the same speed and can be acted on exactly as little, and the difference between the two scenarios is entirely in how the people aboard feel for the remaining 1,000 years. What the delay really removes is not information but authority. The ship cannot be commanded, only informed. No agency on Earth can direct it, correct it, recall it, or overrule it, because any instruction arrives long after the moment it addressed. The relationship between a mission and the people who sent it has never worked this way before and has no terrestrial equivalent. The sponsors become, within a single lifetime, an audience. There is a version of this that is harder to sit with, and it should be said plainly rather than dressed up. Nothing obliges the transmissions to continue. They arrive for a century and another, and the ship's people grow up hearing news, music, argument and science from a place they have never seen and cannot answer. And then, in some year, they might simply stop. There would be no explanation, because an explanation would itself take 11.9 years to arrive and would require somebody still there to send it. There would be no way to distinguish between a civilization that ended, a civilization that lost interest, a civilization that changed its technology, and a receiver aboard the ship that quietly failed. All four look identical from the inside, a channel that used to carry something and now carries nothing. The ship would go on regardless. It has to. But the possibility that the silence is permanent and that nobody aboard will ever learn which of the four it was is one of the mission's real unknowns, and it is not an engineering problem. It is simply what 11.9 light-years does to a relationship. Slowing down is the expensive half of the voyage, and it always was. The reason sits in the same arithmetic that shaped the departure. Propellant used at the far end must be carried from the near end, which means it must itself be accelerated, which means more propellant is needed to accelerate it. The requirement compounds, and the result is that the mass ratio needed to stop at a destination is roughly the square of the ratio needed to fly past. Every kilogram that arrives at Tau Ceti at rest was bought and paid for 1,200 years earlier, on terms nobody aboard can renegotiate. There is no possibility of skipping it. At 1% of light speed, a ship crosses an entire planetary system in a matter of weeks. A flyby of Tau Ceti would return a few weeks of data and then continue outward forever, carrying everyone aboard into a second crossing they did not plan and cannot supply. The stop is not the conclusion of the mission. It is the mission, and it is not an event. At any deceleration gentle enough for people to live through comfortably, shedding 3,000 kilometers per second takes years, plausibly decades. There is a braking generation, people born into a world that is slowing down, who spend their entire lives with the apparent direction of down slightly tilted, exactly as the first generation did during the departure burn. Their parents remember a level floor. Their children will know one. They will not. They are also the first people in 12 centuries to find out whether the engines still work. Everything the ship has done since the first year has been coasting. The propulsion system has been inspected, maintained, and never used by 40 generations who had no way to test it without spending the fuel it exists to burn. The first firing is the only firing that matters. That is the braking problem as it has always been described. But at Tau Ceti there is a second one, and it is not about the ship at all. Remember the debris disk? At the start of this journey, it was introduced as the single best thing about the destination. More than 10 times the cometary and asteroidal material of the solar system, a vast reservoir of water, carbon, nitrogen and metal, sitting in gravity wells so shallow that a spacecraft could take what it needed and leave without spending anything worth mentioning. A civilization arriving there would not have to land on a planet to survive. It could simply reach out and take what was already loose. All of that is still true. Not one word of it needs revising. It is also, without any change to the underlying fact, the reason the arrival is the most dangerous part of the entire voyage. Consider what the ship has just done. It has crossed 11.9 light-years of a medium holding 3/10 of a particle per cubic centimeter, emptier than anything human beings know how to manufacture. In 1,200 years of travel through that emptiness, essentially nothing has happened to it. The erosion was measured in fractions of a millimeter. The impacts were rare and survivable. The one persistent hazard, cosmic radiation, was answered by putting mass in the way and has been answered the same way since the first year. And now it has to decelerate, over years, inside a belt of debris an order of magnitude richer than the one we live in. The disk's inner edge sits somewhere around 6 times the Earth-Sun distance, and its emission extends out to roughly 44, with earlier work suggesting material as far as 55. The dust in it is not left over from the system's formation. It cannot be, because dust that old would have been swept away long ago. It is being manufactured continuously, right now, by collisions between larger bodies. The belt is not a static hazard sitting in space. It is an active one, generating fresh debris on a permanent basis, and it has been doing so for 8 to 10 billion years. Every factor that made the crossing survivable reverses on arrival. Impact energy falls as the ship slows, which genuinely helps. But exposure time rises enormously, and it rises far faster than the energy falls. The ship spent the crossing moving through nothing very quickly. It spends the braking era moving through something slowly, and then it stays there. A hazard you pass through at speed is a different kind of hazard from one you decelerate inside for a decade and then live in. The ship is also at its most vulnerable in every other respect at exactly that moment. Its shielding geometry was optimized for the forward direction, and during braking the engines are firing forward, which means the protected face and the working face are in conflict. Its structure is under load for the first time in 12 centuries, rather than coasting. Its margins have been spent. Its propellant reserve, which was the ship's only capacity to respond to anything, is being consumed on schedule and will be gone when the maneuver completes. And there is no corridor to thread. The observations constrain the belt's width relative to its own radius, and it is broad, at least 3/4 as wide as it is far out. This is a diffuse zone, spread across tens of times the Earth-Sun distance, not a narrow ring with a clean gap inside it. Worse, a belt that broad and that unstructured is usually read as evidence that no large planet is sculpting its inner edge, which removes the one natural mechanism that might have swept a lane clear. The framing to hold on to here is not irony, and it should not be delivered as though the universe had arranged a trap. It is one physical property of a star system, read twice by people asking 2 different questions. Ask what raw material is available at Tau Ceti, and the answer is 10 times what we have, all of it accessible. Ask what the impact environment is at Tau Ceti, and the answer is 10 times what we have, all of it in motion. Those are the same sentence. The abundance is the hazard. There is no version of that system which is rich in resources and quiet at the same time, because the richness is measured by the collisions. There are ways to brake that do not spend propellant, and they are worth knowing about, because they change the arithmetic considerably. A magnetic sail generates drag against the charged particles of the interstellar medium, and its authority is greatest at high speed and fades as the ship slows. An electric sail behaves in the opposite way, working best at low speeds. Handing off from one to the other has been argued to bring a ship down from a few percent of light speed in a few decades, rather than the better part of a century for either alone. There is also the possibility of using a star's own light pressure to decelerate, which requires no propellant whatsoever and which caps the usable arrival speed at a few percent of light, comfortably above the 1% this ship is traveling at. Any of those would reduce the propellant burden enormously. None of them reduces the time spent inside the disk. In fact, they lengthen it. It is worth noting what failure looks like here, because it is not what the word suggests. A ship that cannot brake does not crash into anything. The system is far too empty for that, even at 10 times our density of debris. It simply passes through Ceti over a period of weeks, takes whatever observations it can, and continues outward into the space beyond at the same speed it has held for 12 centuries. The mission does not end in a collision. It ends by not ending, by becoming a permanent condition rather than a journey, carrying a population that now has no destination and a supply of everything sized for a trip that is already over. Which is why the sensible plan on arrival is almost certainly not to go anywhere near a planet. The obvious first act is to match velocity with the system and take up a station well outside the belt, in the quiet region beyond the debris, and survey the place properly for the first time in the history of our species. That survey could reasonably take decades. There is no hurry, and there is a great deal to learn, and the ship remains a functioning world for as long as it is maintained. Nothing about arriving requires anybody to descend to anything. And there is one more consequence of that abundance, which belongs to the destination rather than to the ship. Any planet in that system has been absorbing impacts at an elevated rate for 8 to 10 billion years. Not occasionally. Continuously, over a span nearly twice the age of the Earth. Whatever surfaces are down there have been resurfaced, repeatedly, by events far more frequent than the ones that have shaped our own world. That is a navigation problem for an arriving ship. It is a much larger question for anything that might have been trying to live there. The candidates are candidates. It is important to say that clearly, because the language around exoplanets tends to promote possibilities into facts, somewhere between the measurement and the retelling. What exists is 4 periodic signals in the motion of a star. Cycles of about 20 days, about 49 days, about 160 days, and about 642 days, each interpreted as the gravitational tug of an unseen body. The implied minimum masses run between roughly 1 3/4 and 4 times the mass of the Earth. And the 2 outermost signals sit near the inner and outer edges of the optimistic habitable zone, which is a genuinely interesting place for a pair of planets to be. It is also several steps short of knowing anything about them. The method used to find them measures the star's motion toward and away from us, which means it is only sensitive to the component of a planet's pull that lies along our line of sight. If a system is tilted so that its orbits are seen edge-on, that component is the whole of the pull, and the mass derived from it is the true mass. If the system is seen face-on, the orbits are almost perpendicular to our view, the detectable component is small, and the same signal implies a much larger planet. The measurement therefore gives a flaw and not a value. Every mass quoted for these worlds is a minimum, and the true masses could be substantially higher. And Tau Ceti's debris disk is seen almost exactly face-on. Disks and planets in a system generally share an orientation because they formed from the same rotating cloud. If the planets share the disk's alignment, the system is close to face-on from our point of view, which means the minimum masses may be considerable underestimates. The worlds that look like super-Earths might be a good deal heavier than that. Nothing about the observations rules it out, and the geometry of the disk actively suggests it. The same geometry closes off the other main route to knowledge. Most of what is known about exoplanets in general comes from watching them pass in front of their star and measuring the dip in brightness, which gives a radius directly. That only happens for systems aligned edge-on to us. A face-on system never transits from here, ever. Which means Tau Ceti's planets cannot be sized by the standard method, cannot have their densities computed, and cannot have their atmospheres read in the usual way, no matter how long anyone waits or how good the instruments become. There is a real possibility that the ship's own instruments are the first things in the history of the universe to measure the radius of a planet at Tau Ceti. Even a confirmed mass and a confirmed radius would leave the composition ambiguous, which is a fact that gets lost in the reporting of exoplanet discoveries. Density is a single number, and many different worlds produce it. A given density is equally consistent with a rocky planet carrying a thin atmosphere, and with a smaller rocky planet wrapped in a thick envelope of light gas, and with several intermediate cases involving different amounts of water. The measurement does not distinguish between them. Something has to break the tie, and the only reliable tiebreaker is going and looking. The star's chemistry adds further caution. Tau Ceti's iron content is about a third of the Sun's, and planets are built from the same material as the star they orbit. A system short of heavy elements is a system short of the iron and nickel that make up a planet's core, and much of what an arriving civilization would want to build with. And there is that unusual ratio of magnesium to silicon in the star's light, which, if inherited, would give its world's mineralogies genuinely unlike Earth's. That reaches further than it sounds. The minerals in a planet's mantle determine how easily its interior flows, which determines whether it has plate tectonics, which determines whether it has the slow cycling of carbon between rock and air that keeps a climate stable across billions of years. A world with the right mass, in the right orbit, around the right star, can still fail to be habitable for reasons that live in its rocks. The phrase habitable zone deserves a moment of skepticism too, because it is doing less work than it appears to. It describes an orbital distance and nothing else. It is the range where a rocky planet with a suitable atmosphere could hold liquid water on its surface, and every one of those qualifiers matters. There are at least 3 definitions in common use, with different assumptions about clouds and atmospheric composition, and they give noticeably different boundaries. Tau Ceti's outer candidate falls inside the zone on the optimistic definition, and outside it on the conservative one. That is not a disagreement about the planet. It is a disagreement about the definition, and the planet is unaffected by either. In fairness, Tau Ceti does avoid the single largest problem afflicting most nearby habitable zone candidates. Around the red dwarf stars that dominate the solar neighborhood, the habitable zone is so close to the star that any planet in it becomes tidally locked, one face permanently toward the star, one permanently away, with a fixed line between them and a permanent wind blowing across it. Around a star like Tau Ceti, the habitable zone sits far enough out that this does not happen. A world there would rotate and have days and distribute its heat the ordinary way. That is a genuine advantage, and it should be credited. The debris also gets in the way of finding out more, which is an inconvenience with real consequences. Dust in a system scatters starlight, and a system with 10 times our supply of dust glows correspondingly brighter in exactly the wavelengths where anyone would try to image a planet directly. The planets are faint, the dust around them is not. Every future attempt to photograph a world at Tau Ceti has to contend with a haze that our own system does not impose on observers looking at us. The richest system on the shortlist is also one of the hardest to examine. And there is a distinction that matters enormously and is almost never made, which is the difference between a planet that has an atmosphere and a planet that has a breathable one. Those are separated by an enormous margin. Carbon dioxide, for instance, becomes dangerous to a human being at concentrations far below 1% of an atmosphere, a level that would not even register as a notable component in a remote spectrum. A world could be reported accurately as having an atmosphere, a temperature within range, and water present, and still be somewhere a person could not draw a single safe breath. Remote observation is very good at detecting the presence of things, and very poor at establishing the absence of the things that kill you. Which suggests a better question than the one usually asked. The practical test of any world at Tau Ceti is not whether it is habitable. It is whether it is useful, whether it has material worth extracting, a surface worth working, an orbit worth occupying, a magnetic field worth sheltering under. Those questions have answers that instruments can find, and that do not depend on the world being anything like Earth. A civilization that has spent 1,200 years living successfully inside a machine has already demonstrated that it does not require a planet. What it requires is supply. There is one further trap worth naming, because it is the trap most likely to produce a false celebration. Detecting oxygen in a planet's atmosphere is not proof of life. Oxygen can accumulate without biology, when ultraviolet light from the star splits water molecules and the lightweight hydrogen escapes to space, leaving the oxygen behind. On a world losing an ocean, this happens readily. From 12 light-years away, telling that case apart from a living one is extremely difficult. From inside the system, with instruments in the atmosphere itself, it is a solvable problem. That distinction between a signal and a determination is most of what the voyage is actually for. So what should anyone expect to find? Not, most likely, a habitable planet. The odds against any particular star having a world where a human could stand outside are long, and the specific concerns at Tau Ceti, the elevated impact rate, the low metal content, the unusual rock chemistry, the real possibility that the candidates are heavier than they look, all push in the same direction. Not, most likely, a barren system either. What the evidence actually describes is a stable, quiet, extremely old star, with several small worlds in reasonable orbits whose nature is unknown, surrounded by an enormous and easily accessible supply of water, carbon, nitrogen, and metal in the form of comets and asteroids. Which is to say, the most probable outcome at Tau Ceti is not a landing. It is a settlement built from local material, in orbit, using exactly the abundance that made the arrival difficult. The people who came 12 light-years to reach a new world would live, as their ancestors did, inside something they built. The difference is that they would be building it from Tau Ceti's material around Tau Ceti's star, with sunlight instead of a reactor and no destination left to reach. Whether that counts as arriving is a question the mission plan cannot settle, and the people aboard will not have the option of asking anyone. Before the ending, the other side of the ledger, given in full, because a 1,200-year voyage described only through its difficulties is not being described accurately. The middle centuries are not a punishment. The people living through them have a complete world, with real work in it that genuinely needs doing, and the knowledge that it needs doing. They have a social environment as rich as any small town that has ever existed. Friendships, rivalries, families, music, argument, invention, everything a few thousand people generate when they live together. They have environmental stability no terrestrial population has ever enjoyed. No drought, no storm, no flood, no crop failure that is not a design failure somebody can address. No war over territory in a place with no territory to contest. They have an unambiguous shared purpose, which is rarer and more valuable than comfort, and which most human beings who have ever lived did not have. And they have no basis for comparison, which is not a deprivation. A person born in the 4th century of the Crossing is not missing Earth. They have never seen it, never wanted it, and have no more sense of loss about it than anyone reading this has about the places they were never going to visit. They are living in the only world they have, doing necessary things, among people they know, in a place that was built to be lived in rather than merely survived. That is a good deal more than a great many human beings have managed, and it should not be described as a sacrifice by people who are not making it. There is even a case to be made that the ship is the safer place. Nothing aboard is left to chance, because nothing aboard can afford to be. The air is measured continuously. The water is accounted for by the gram. The food supply is not subject to weather, the population is not subject to invasion, and the failures that do occur are understood in advance by people whose entire education was about understanding them. Earth is a wonderful place to live, and it has never once guaranteed anybody anything. A well-run generation ship, for all its fragility, is a place where the things that could kill you are known by name and watched by somebody whose job it is. And if more than one ship was sent, which is the sensible way to do this, and the way most serious proposals assume, then the middle centuries contain something the picture so far has left out. Another vessel, in formation, within easy reach. Another society to compare notes with. Another set of children growing up under the same rotation. Somewhere for a person to go who cannot stay where they are. 2 ships is not twice 1 ship. It is a different kind of life, and it removes most of the loneliness from the arrangement without changing a single number in the mission plan. The generation that arrives has its own particular difficulty, and it is worth acknowledging rather than glossing over. They are the first people in 40 generations to be handed a completed task. Everyone before them inherited a voyage and passed on a voyage. They inherit a voyage and hand on something else entirely. A place, a survey, a decision, a whole set of questions their ancestors never had to hold. 1,200 years of culture built around continuing has to become, within a single lifetime, a culture built around choosing. That is a real transition, and there is no manual for it aboard. Now the ending. At the very beginning of this journey, one small fact was set down and left alone. Tau Ceti is not where it appears to be. It crosses the sky at about 1.9 arcseconds a year, and it is approaching along the line of sight at about 17 kilometers per second, and so the ship could not be aimed at the star. It had to be aimed at a prediction of where the star would be. Here is what that prediction contained. Over 1,200 years, moving toward us at 17 kilometers per second, Tau Ceti closes about 4,200 times the distance from the Earth to the Sun. That is roughly 7/100ths of a light year, something like 25 light days. At 1% of the speed of light, it is about 7 years of travel that the ship never had to make. The gap did not simply sit there waiting to be crossed. It shrank continuously for the entire duration of the voyage at a rate nobody aboard could influence and nobody aboard could stop. And in the same 1,200 years, the star slid more than half a degree sideways across the sky, a distance a little wider than the full moon looks from the ground, which is precisely why the ship had to be aimed at a prediction in the first place. So this was never a journey to a fixed place. It was a rendezvous. Two objects, 12 light-years apart, approaching each other for 12 centuries, one of them carrying 40 generations of human beings and requiring continuous, unbroken, unforgiving maintenance for every hour of it, every seal replaced, every crop pollinated by hand, every bearing rebuilt, every skill taught to somebody who would teach it to somebody else, and the other requiring nothing at all. The star did about 6% of the work. It did it without a crew, without a plan, without a repair schedule, and without ever knowing anything was coming. It is worth holding that proportion for a moment, because it is easy to hear as a small joke, and it is not one. 7 years out of 1200 is not much. But it was accomplished by an object that made no effort, took no risk, kept no schedule, and had no idea the arrangement existed. Everything else, every hour of the other 1,193 years, had to be earned by people who woke up each morning inside a machine and kept it working. The ship supplied the effort. The star supplied only its motion, which it would have supplied anyway. There is one more turn to make, and it uses a number that has already been used twice. 11.9. It began as a distance, the gap between the Sun and Tau Ceti, measured in light years. It became a delay, the price in years of every question the ship asked of home. At the moment of arrival, it becomes something else again, and this time it becomes permanent. Standing at Tau Ceti, everything visible of Earth is 11.9 years old. Everything visible of Tau Ceti from Earth is 11.9 years old. That is not a technical limitation, and it will never be improved upon. It is the fixed offset by which the two halves of our species will be out of step with one another for as long as both of them exist. Whatever happens at Tau Ceti, whether the arrival succeeds, whether the settlement holds, whether anybody is alive to send word, the news takes 11.9 years to reach anyone who might care, and by the time it does, the people who launched the mission have been dead for more than a millennium. The first act on arrival, if there is one, is almost certainly not a landing. It is to match velocity with the system, take up a station in the quiet space beyond the debris, and look, properly, closely, from inside, for the first time in the history of anything our species has ever done. That survey might take decades. There is no hurry. The ship is still a world, and it will go on being one for as long as it is maintained, which is the same thing that has been true since the day the last supply vessel turned away. And the disk will still be there, glowing faintly in the cold, 10 times richer than anything at home, grinding itself into dust, making the material that everything afterward would be built out of. 1,200 years. 11.9 light-years. 40 generations, none of whom saw both ends. 1% of the speed of light, held steadily, without adjustment, through a space so empty it left the ship almost entirely alone. And so the two of them go on approaching each other in the dark, the ship and the star, the way they have been doing since long before anyone alive was born. Nothing about that needs watching tonight. Let your breathing slow. Let the distance stop mattering. Sleep well, and good night.